All we talked about so far was for zero launch angle. Now, in this section, let's consider the case of a projectile launch and at an arbitrary angle with respect to the horizontal. Okay, let's consider a case that this is x, y, this is my zero, and the projectile is moving with this initial velocity here. So if I'm shooting something in this direction, I kind of like expect a projectile to move like this. So the launch angle is theta here. Okay. So because I set up the origin at x equals to x naught equals to y naught to 0, and this is our assumption, or this is how I set up my coordinate system, then I know that the initial v it has both components, x and y, because the launching angle is not 0 anymore. So, and then I know that in x direction, v naught is equal to v naught cosine theta, and in y direction, the initial velocity is equal to v naught sine theta. Okay, so let's just quickly check. So if the launching angle is 0, then v naught x is going to be 0, and v naught y is going to be v naught, right? Sorry, if completely say the opposite. So if theta is equal to 0, then I can say that v naught x is going to be v naught and v naught y is equal to 0. So this is what we had so far. If I'm shooting the projectile upward, which means that theta is equal to 90, then v naught x is going to be 0 and v naught y is going to be v naught. Okay, so this is another case for later. Now, if I have both components, which means that the initial velocity has an angle corresponding or with respect to the horizontal, then I can use the equation, the basic equations of motion that I had, and then substitute the preceding results into those basic equations. Then I get x equals to, it was v naught x times t, so it's going to be v naught cosine theta times t. So this is one set of equation in x direction, and then Vx equals to V naught cosine theta, and then Vx squared equals to V naught squared cosine squared of theta. So this is for x direction, and then in y direction, y equals to V naught sine theta, so this is V naught y, times t minus half gt squared, and then v in y direction is going to be v naught sine theta, which is the v naught y part, minus gt, and vy squared equals to v naught squared sine theta squared minus 2g delta y. Alright, so three more for the y direction, and all of this is called equation 410 on your book. So basically what we are doing is that we talked about the basic equations for the projectile motion. Then we went ahead and just solved some problems or gave some equations for the specific case of launching angle equals to 0. In this section, I'm just taking those basic equations and I'm considering just like an arbitrary angle which is non-zero. Now let's solve a quick example on this so that you see nothing has changed. It's just like instead of the initial velocity only being in x direction, now I have the initial velocity that has both components because it has an arbitrary launching angle. this example says that a projectile is launched from the origin with an initial speed of 20 meters per second at an angle of 35 degrees above the horizontal. Okay, so V naught is going to be 20 meters per second, and then theta is 35 degrees above the horizontal. It means that it's positive. So this is the known. Find the x and y position. So the unknown is x and y at times. Let's just solve for t equals to half second. Okay, so I'm using this equation, x equals to v naught cosine theta times t, and then I'm replacing it. So it's going to be 20 meters per second cosine 35 degree times half second. Substituting these numbers, x equals to 8.19 meters. To find y, the equation that I'm using is y equals to v naught sine theta times t minus half gt squared. And I know that g is equal to 9.81 meters per second squared. So substituting the numbers here, y equals to 20 meters per second sine 35 degree times half second minus half times 9.81 meters per second squared times half second squared. Okay, solve this, and then y is going to be 4.51 meters. Okay, now if it asks me to find the velocity of the projectile at this time, so if it asks me, this is like an extra part, that I want to find the velocity of projectile. So what is the velocity? So I know that I need to find Vx and Vy separately. So I know that v in x direction is only v naught cosine theta, because then the acceleration, or the acceleration due to gravity does not affect this. So v in x direction is only 20 meters per second time cosine 35 degree. So vx is 16.4 meters per second. Okay, but when it comes to y component of v, then the gravity affects here. So I know that vy then equals to v naught sine theta minus gt. So this is an extra term that it has in y direction. So vy is 20 meters per second sine 35 degree minus 9.81 meters per second square times half seconds. Okay, so v in y direction is 6.57 meters per second. So you see how the x component of velocity is not being affected by time, right? Because this second term simply does not exist when we are talking about Vx. Vx is always V naught cosine theta. So it only depends on the initial velocity and on the angle or launch angle. All right, so I can write V in its component form, so 16.4 meters per second in x direction plus 6.57 meters per second in y direction. So this is the velocity at time equals to half seconds. There are several examples on your book. On the page, let me see, on the page 100, 101, 102, and 103. I want you to go ahead and study them on your own. And let's talk about section 4.5, the key characteristics of projectile motion. Okay, first of all, we are going to draw a picture here. Actually, it's better if I do it on the next page so that you can see the equations and the sketch all together. Okay, let me go to the other page. All right, so X and Y, origin here. The projectile initial velocity is in this direction. So the path will be something like this. Oops, I need to extend my X. Okay, so here it lands somewhere around here. Okay, and this is the launch angle, which is theta. Now, so the first thing that we want to know or define is range. So this is very similar to the landing site, right? So this we call R, and then it is called the range. So the range of a projectile is the horizontal distance it travels before landing. Okay, so for this, or to find this, I'm gonna put y equals to 0 because it is where it lands, so it doesn't have the height anymore. Okay, the initial elevation occurs at t equals to 0 when the projectile is launched, and then the projectile returns to the same elevation at a later time when it lands. Okay, so one way to obtain the range is like this. First of all, find the later time when the projectile lands by setting y equals to 0. So I'm using this expression, y equals to v naught sine theta. This is the initial velocity in y direction times t minus half gt squared. Okay, so I'm going to put y equals to 0. So 0 equals to v naught sine theta times t minus half gt squared. So this means that v naught sine theta times t equals to half gt squared. Okay, so then we need to solve this equation. Okay, so obviously t equals to 0 is one one solution to this equation. So it has two solutions. T equals to 0 is the first one, and that corresponds to the initial condition. But another solution that it has is by canceling this t with the squared here, and then I can write v naught sine theta equals to half gt, or t equals to 2 v naught divided by g sine theta. Okay, so this is another solution. Okay, so this is the time when the projectile lands. So time of landing, meaning the time that occurs here. So this is equation 411 on your book. Okay, now I substitute this time into x equals to v naught cosine theta times t to find the range. So this is going to be V naught cosine theta multiplied by 2 V naught divided by G sine theta. Okay, so I'm going to rearrange this. Then x becomes 2 V naught squared divided by G sine theta times cosine theta. Alright, so this x is range. So I can write range to be 2 V naught squared divided by G sine theta cosine theta. Now, we have a trigonometric identity that says sine 2 theta, so this is a subnote, equals to 2 sine theta cosine theta. Okay, so this is the identity that I know. Now this you can find on in Appendix A. So Appendix A gives you all the trigonometric identities that is useful in this book. Now I can write then sine theta times cosine theta to be sine 2 theta, sine 2 theta divided by 2, and I can use this to find range to be V naught squared divided by G sine 2 theta. Okay, so this is when the projectile goes back to the final elevation that is same as the initial elevation. All right, now that I know the equation for the range, what launch angle gives the greatest range? So here we're talking about maximum range. For example, if you're in a shooting field, this is important to know, right? So that what launch angle you need to have so that you can have the greatest range. So we call this R max. So obviously R max happens to be V naught squared divided by G when sine 2 theta is equal to 1, right? So this means that, like the greatest value that a sine can ever have is 1. It's a positive 1, and the minimum that it can have is negative 1. So when sine 2 theta is equal to 1, then you have the maximum of range. So we know that sine 90 is equal to 1. So this means that theta is 45 degree. So at 45 launching angle, we have the maximum range, which is V squared divided by G. So this is equation 413 on your book. And of course, this is an ideal situation when there is no air resistance. Okay, so if there is an air resistance, which is in like our life, in our daily life, then that is going to be different. But here for this book, because we are neglecting the air resistance, then we can say that the launching angle equals to 45 degrees has the maximum range for the projectile. Another important topic that we need to note here is the symmetry in projectile motion. Okay, so this is interesting, kind of. So there are many symmetries in projectile motion, beginning with the graceful symmetry of the parabola itself. Okay, so recall that the time when a projectile lands was equal to 2 V naught divided by G sine theta. Now, recall that when a projectile is launched, its y component of velocity is Vy equals to V naught sine theta. When the projectile lands at t equals to this expression here, then the y component of velocity becomes vy equals to, so this is at launch, so this is at launch, and this is at land. So v naught sine theta minus gt. So this is when it lands. All right. So I can write this Vy to be V naught sine theta minus G, and I'm replacing T here to V naught G divided by G sine theta. So you see how these two guys cancel, and then I get Vy to be V naught sine theta minus 2 V naught sine theta. It's going to be negative V naught sine theta. Now compare these two. So the first one is when we launch the projectile. This one is when the projectile lands. So this is exactly the opposite of the y component of the velocity when it was launched. Now, since the x component of velocity is always the same, it follows that the projectile lands with the same speed it had when it was launched. The velocities are different because the direction of motion is different at launch and at landing. So there is a nice symmetry with the direction of motion here. If the initial velocity is above the horizontal by angle theta, then the landing velocity is below the horizontal by the same angle. So let me just plot this for you. So if this is x and this is y, all right. So when you shoot this or when you throw this at any time, so there is this nice symmetry here for the velocity. So if you shoot, so if like for example at time, let's say whatever, the velocity has both vx and, so this is the velocity here, and then this is theta, and here is vy, right? So it happens that it has this nice symmetry that when it is coming or landing at any given time, then vx is just same, and then vy is exactly the same, but in opposite direction. Oops, sorry. So this is vx, and so this is vy, and then it's exactly the same angle, but now below the horizon. So this is negative theta, and this symmetry is true in all over the path. So if this is v here, then at this point is exactly the same but in different direction. It happens that at the highest point, it only has Vx. Okay, so with this topic, I'm gonna end this chapter 4, and I want you to go ahead and study the whole section 4. Hold on. So section 4.2, 4.3, 4.5, and 4. Okay, so that is the end. 4.5. So 4.2, 4.3, 4.4, and 4.5, which is about the projectile motion. There are several examples in your book that are very helpful. You have like enhance your understanding parts. And the answers are given at the end of the chapter on the book, so you can actually work on it yourself and then check your answers. And I hope that you find this actually useful in your daily life now when you go out, and if you're just like playing basketball, or if you're even um, like playing golf, or if you do anything that includes throwing a ball. Now you can actually look at the path of the motion, and now you know that it's called projectile motion. You know that it is landing because of the gravity, and you know how symmetric the path of motion is, which is slightly different when we are considering the air resistance, but still you can see how nice and symmetric the path is. And you can even try to test the range and see, like, if you actually throw a ball, if like the maximum range is at 45 degree when you are using it with the air resistance or not. So that could be some simple practice for you. Of course, this is not mandatory. I'm just like giving you some ideas that if you're interested, do that. Go ahead and try to throw the ball with different initial angles. Throw the ball with 0 degree and then raise it slightly above the horizontal level, which could be like 25 degree, and then try 45 degree, and then try 90 degree, and see which one gives you the highest range. Now, if you ever get like interesting results, please email me, or even you are more than welcome to put it in the discussion, your experiment, and that will bring you a bonus point. Well, good luck.